Okay friends, after the Taylor's series expansion, let's come to Laurent's expansion. We know the Taylor's expansion is valid for analytic functions. That is, every analytic function can be expanded in a Taylor series around a point z0 at which the function has no singularity. But you can also expand functions in regions in which the singularity exists. That produces the Laurent series. A Laurent series in the standard form for a function f of z around z0 appears like this. Please observe that there are two segments. In segment number 1, you have only positive powers of z minus z0, and this part is known as the Taylor's part or the analytical part. The second part, which contains negative powers of z minus z0, is known as the principal part. In fact, it is the principal part which is highly used in contour integration, and particularly for n is equal to 1, the coefficient b1 is a coefficient of 1 by z minus z0 in the Laurent's expansion, and this is called the residue of f of z at z is equal to z0. Another issue which comes up is the nature of the principal part. If we have no principal part at all, that is all bn or 0, then only this part is left out, and then the function simply represents the Taylor's expansion. On the other hand, if this term contains infinitely many number of terms, then z0 is called a singularity, which is specifically called an essential singularity. When we have limited powers of z minus z0 to the power of n, then the z0 is called a pole. Of course, once you come to the concept of pole, the question of order also comes. It all depends upon the power n of that particular pole. That is, if the principal part contains 1 by z minus z0 whole square as the highest, then 2 is called the order of that pole. It is called a double pole. On the other hand, when n is equal to 1 and it stops there, then z0 is called a simple pole. Otherwise, it is called a pole of order n plus 1. So, before we come to the issue of pole and residue calculations, let us do a couple of problems on the Laurent's expansion. In this exercise, we wish to watch and see what is happening to the principal part, and there may be a couple of problems where we may have to talk about order of the pole, nature of the pole, and so on and so forth. Question number 6. What is the Laurent's expansion of 1 by z plus 1 into z plus 3 in the region mod z greater than 3? So, first get the partial fractions of this function. Let 1 by z plus 1 into z plus 3 is equal to a by z plus 1 plus b by z plus 3. A is equal to 1 by minus 1 plus 3, which is half. B is equal to 1 by minus 3 plus 1, which is minus half. So, f of z can be written as half of 1 by z plus 1 minus 1 by z plus 3. It is now you must look at the region. Whenever you expand, you must expand it in such a way that the function converges within that region. So let us see how to plan this. Now, mod z greater than 3 implies mod z by 3 is greater than 1. This implies mod 3 by z is less than 1. That's a very important thing. And when mod 3 by z is less than 1, this implies mod 1 by z is also less than 1. When 3 times a quantity is less than 1, 1 times that will also be less than 1. Now, why did we write this from there? Because we have two partial fractions here. One of them connected to this one, the second one is connected to that. So, from here, if you have to get 1 by z, so you have to take z common from there, half of 1 by z into 1 plus 1 by z. And again from here, if you want 3 by z, again you must take z common. So please observe, creation of 1 by z and 3 by z become necessary because only in this regions you can have a convergent series. So this can be written as 1 by 2z into 1 plus 1 by z whole inverse minus of 1 plus 3 by z whole inverse. These are simple binomial expansions. This will be 1 minus 1 by z plus 1 by z squared minus 1 by z cube and so on, minus of 1 minus 3 by z plus 9 by z squared minus 27 by z cube and so on. So simplification of this should give us a result 1 by 2z into this one and this minus 1 will get cancelled. 3 by z minus 1 by z is 2 by z. 1 by z squared minus 9 by z squared is minus 8 by z squared. Then minus 1 by z cube plus 27 by z cube is 26 by z cube and so on. So if you reduce this, you will find that option D should be matching. So please check, you will have to just take the 1 by z inside and cancel the 2's here and you will find option D is the correct answer. So the first important thing is partial fractions. After the partial fractions are obtained, you see what is the region given to you. You make it a less than 1 situation, and because there are two fractions, you have to do two such things, one for this fraction, one for this fraction. So mod z greater than 3 will give us mod 3 by z less than 1, from which you must derive this one so that you can operate on this fraction. Expand, of course you must be good in binomial expansions, and then simplification. So this is how one must solve questions involving partial fractions. Question number 7. What is the coefficient of z squared in the Laurent series of sine hyperbolic 3z by z cube? All of us know complex functions can be expanded in Laurent series given a certain domain. Now let us look at this one. We know sine hyperbolic theta has an expansion theta plus theta cube by 3 factorial plus theta power 5 by 5 factorial and so on. So here theta is 3z. So therefore, if you take sine hyperbolic 3z by z cube, this will be 1 by z cube into 3z plus 3z whole cube by 6 plus 3z whole power 5 by 120 and so on. So 1 by z cube into 3z plus 27 by 6, that becomes 9z cube by 2 plus 3 power 5 is 81 into 3, z to the power of 5 by 120 and so on. So let's do some simplification. 3 cancels 40 times. Now you take 1 by z cube into the bracket. You will have 3 by z squared plus 9 by 2 plus 81 by 40 z squared and so on. We need the coefficient of z squared in the expansion, and the coefficient of z squared in the expansion is 8 by 40, and the option is B. Question number 8. Another problem on Laurent series. How many number of terms will be present in the principal part of the complex function 1 by z plus 1 into z plus 3 valid in the domain 0 less than mod z plus 1 less than 2? Now the first step is to resolve this into partial fractions and then take into account the domain. So you let 1 by z plus 1 into z plus 3 is equal to a by z plus 1 plus b by z plus 3. So a is equal to 1 by minus 1 plus 3, which is half, and b is 1 by minus 3 plus 1, which is minus half. So f of z is equal to half of 1 by z plus 1 minus 1 by z plus 3. Now you can see very clearly from here that z is equal to minus 1 is the center of expansion, because we will have to visualize this as 0 less than mod z minus of minus 1 less than 2. Well, what is very important is to take z plus 1 as a reference. Now you can see that z plus 1 is actually here, so we must not manipulate this one. On the other side, we must manipulate this in terms of z plus 1. Now where is the domain? The domain is here. So when mod z plus 1 is less than 2, this implies mod z plus 1 by 2 is less than 1, which is a very important thing for convergence. So you will have to write f of z very carefully like that. We don't have to touch this because it's matching with the center of expansion. So f of z is equal to half of 1 by z plus 1 minus 1 by z plus 1 plus 2. Now because we need z plus 1 by 2, you take 2 outside here. So f of z is equal to half of 1 by z plus 1 minus half 1 by z plus 1 by 2 plus 1. So half of 1 by z plus 1 minus half into 1 plus z plus 1 by 2 whole inverse. So you can expand that using binomial theorem, and you will have half of 1 by z plus 1 minus half of 1 minus of z plus 1 by 2 plus z plus 1 by 2 whole squared, and so on. Now all of us know from the theory of Laurent series that after expansion, generally there will be 2 segments. One part consisting of the positive powers of z or z plus a, and the other part is negative powers of z plus a. Now the principal part is basically that part consisting of the negative powers of z plus a. So if you count, this is the only term having negative powers of z plus 1. All other terms are positive powers of z plus 1. Therefore, the principal part consists of only one term, and this corresponds to option B. Question number 9. Where are the simple poles of f of z is equal to z power 4 by z power 4 plus 1 located? Now this is a rational algebraic function, and therefore the singularities that you get are basically the poles. Now what is the definition of a singularity? A singularity is that point or those sets of points where the function is undefined. So you can see that the poles are the solutions of poles of f of z are solutions of z power 4 plus 1 is equal to 0. All of us know we are in complex analysis, therefore this equation produces 4 values of z. So you are going to have 4 poles. Whether all of them are simple or not, we'll discuss later on. But the general structure of this factorization should be something like z minus alpha into z minus beta into z minus theta into z minus phi is equal to 0. If at all we can get this alpha, beta, theta and phi, those are the singularities. And because these are all of power 1, alpha, beta, theta and phi will be the simple poles. In fact, that is what we are trying to do. If you can factorize this, then all of them will be simple poles. But how to solve this equation effectively? There are 2 approaches, but I'll give the one that produces results in a standard way. You take z power 4 is equal to minus 1, and you know minus 1 can be written as e power I pi, because this is cos pi plus I sin pi. Sin pi you know is 0, but cos pi is minus 1. To this you add a 2k pi with k is equal to 0, 1, 2, 3. For example, for k is equal to 0, you can prepare a table here, and if you look at this equation, z can be written as e power I pi by 4 into 1 plus 2k. Now this is very important for us. So if you can now prepare a table, z is equal to e power I pi by 4 into 1 plus 2k, you will get the poles. For example, for k is equal to 0, you will get e power I pi by 4. And e power I pi by 4 is nothing but cos pi by 4 plus I sin pi by 4. Let us remember e power I theta is equal to cos theta plus I sin theta. Accordingly, you will have cos theta is cos pi by 4, 1 by root 2, sin pi by 4 is also 1 by root 2. So we will have 1 plus I by root 2. So this is one of the poles. For k is equal to 1, this becomes e power I 3 pi by 4, cos 3 pi by 4 plus I sin 3 by 4. So we will get minus 1 plus I by root 2. For k is equal to 2, this becomes e power I pi by 4, that is cos 5 pi by 4 plus I sin 5 pi by 4. So we are in the third quadrant, so both will be negative, minus 1 minus I by root 2. And finally, for k is equal to 3, you get e power I 7 pi by 4. We are into the fourth quadrant, so you will get minus 1 plus I by root 2. So if you observe all these things, you can say minus, in fact, plus or minus 1 plus or minus I by root 2. All the 4 poles which are simple can be compactly written like this, and you will find that option B is correct. So why this example was chosen is to how effectively solve z power 4 is equal to minus 1 equation. The other hard way of doing this is writing z power 4 plus 1. I will simply write for your reference, avoid z power 4 plus 1 is equal to z square minus I into z square plus I. Then if you have to solve this and this, you will have to get z is equal to plus or minus square root of I plus or minus square root of minus I. But whether you can do this problem, I am not sure, Therefore, to avoid all this, we have taken a very good route of solving like this. So this is how you can handle this problem. Question number 10. What is the principal part of f of z is equal to 1 by 1 minus z into z minus 2 in the annular region 1 less than z less than 2? Now, well, first we have to look at the region. You know, this region in the complex plane consists of two concentric circles, mod z is equal to 2 and this is mod z is equal to 1. So the region in which the expansion is required is this annular region. So this describes 1 less than mod z less than 2. So we'll have to see in this region, if you expand this function, what will be the principal part? So first let's get the partial fractions. 1 by 1 minus z into z minus 2 is a by 1 minus z plus b by z minus 2. So a is equal to 1 by 1 minus 2, which is minus 1. B is 1 by 1 minus 2, which is also minus 1. So f of z is equal to minus 1 by 1 minus z minus 1 by z minus 2. Okay. Now you take this region. You will have to see it in two different ways. In one case, you will have to see this as 1 less than mod z, which implies 1 by mod z less than 1. In the second case, you must see this as mod z by 2 less than 1. The first one, 1 by mod z less than 1, will be required here, and the second one, mod z by 2 less than 1, is required here. So if you have to get 1 by mod z here, I must take z common. Here, if I want z by 2, I should take 2 as a common factor. So please see the contrasting patterns here. So this can be written as 1 by z into 1 minus 1 by z whole inverse, and this can be written as plus 1 by 2 into 1 minus z by 2 whole inverse. If you look at the second block, you never get any negative parts of z here. So therefore, this produces the Taylor's part. And we are not interested in this because we are talking of principal part. So this is the principal part. You need to expand this to look at the options. 1 by z into 1 plus 1 by z plus 1 by z squared and so on, which is 1 by z plus 1 by z squared plus 1 by z cubed and so on. And therefore, this happens to be the principal part. You can find that option B for this problem is correct. Now, why we chose this again is to understand the region, and then partial fractions, of course, that's a normal thing, but how you must pick up your conditions, criteria to expand each fraction. And be very careful. There's a nice separation of Taylor's and principal's part. He's asking for principal part. If it was a Taylor's part, you produce that as the answer. In this principal part, if he says what is the residue, you go to the coefficient of 1 by z, and so on and so forth. So let's go to the next topic.